But when we look at the acceleration of the moon and its orbit or its acceleration toward the Earth, okay, and when we're talking about acceleration toward the Earth of the moon here, we're looking at centripetal acceleration, how it's rotating around the Earth in that orbit. Okay, it was found to be 0.00272 meters per second squared. Okay, it's about 1/3600th of what it is on the Earth. Okay, so the acceleration due to gravity on the moon is about 1/3600th that it is on the Earth's surface. Okay, and you can walk through the math. It's on page 115 in your book if you really, really, really want to look at it. But like I said, the way we get to the end equation is not quite as important, I don't think, right now than our final equation. Okay. So the equation that we're going to end up looking at here is this F equals big G times m1, m2 over r squared. Okay. So he found that after comparing the radius of the Earth, the distance of the Earth to the moon, all this stuff, that the gravitational force exerted by the Earth on any object decreases with the square of its distance from the Earth's core, okay, or from the Earth's center. Okay, so the amount of force due to gravity decreases basically the farther away from you that you get from the Earth's core, or the Earth's center. He also started telling us that the gravitational force exerted on objects depends on the mass of both of those objects. Okay, especially when we're talking about things on Earth, we have to take into account the mass of the Earth, okay, which is ginormous as compared to almost any other object. All right, this is the equation that he came up with, and we're going to talk about what each of these variables mean, what they stand for. Okay, F is the gravitational force, or what we've called it thus far has really been F sub G. Okay, this is our force due to gravity. So F sub G. You can label it that if you want. We're just looking at our force due to gravity here. Our capital G is called the universal gravitational constant. Okay, and this is a number that's constant no matter what equation you use it in, no matter how you use it, with what other objects you use it. This is a constant. Okay, so the constant is 6.67 times 10 to the negative 11th. All right, and our units for this are newtons times meters squared over kilograms squared. And unfortunately, there's no short unit for this like there was for the newton. Units for the gravitational constant aren't quite as important, just as long as we have that number correct. Okay. M1 and M2 are masses of each object. Okay, one of these might be the mass of the Earth, if that's what you're dealing with, or they could be two objects that are attracting each other. Okay, so these are masses of both the objects. And what do you think R is in this equation? Yeah, radius. Okay, I didn't put that on there. We've been over it before. And what units does a radius need to be in? Meters. Meters. Look, in order for G to work, we need to have meters, kilograms. Okay, in order for this constant to work, our units have to be correct and they have to match. So we need to have our distances or our radius in meters. Our masses must be in kilograms. Okay, does that make sense? All right, great. Okay, so I'll give you some time to write this down, kind of start contemplating what you think it means, and we'll discuss it here in a second. So we're going to go ahead and try and plug in these into our equation here. So it says a 50 kilogram person and a 70 kilogram person are sitting on a bench so that their centers are 50 centimeters apart. What's the magnitude of the gravitational force each exerts on the other? Okay, so let's just think, if these two people are sitting next to each other on a bench, they're exerting some sort of gravitational force. Do you think that force will be enough to somehow pull these people together? Like, are they physically going to start moving toward each other? No. Okay, you don't ever start sitting next to someone and just start moving. Okay, that's not how it works. Yeah. Okay, no matter how much that person weighs, you will never start moving toward them. on your own, okay? So let's go ahead and start plugging these in. We'll say M1 equals 50. We'll say M2 equals 75. What else can we pick from our equation? Yeah, what's the radius? 50 or, yeah, there we go, 0.5 meters. All right. So now we'll plug into our equation. F equals big G times M1, M2 over R squared. Our G is our gravitational constant, which is 6.67 times 10 to the negative 11th. Okay, that's a constant that we'll have to know. 50 times 75 over 0.5 squared. Plug in, and we should get an answer with what units? Yeah, good. It should be in newtons. Okay, what do we get for our force? What times?
1 times 10 to the negative 6.
That's what I got. About 1 times 10 to the negative 6. So the objects in this problem don't change. Okay, their masses don't change. The things that change are their force due to gravity and their distance or their radius. Okay, so I want to try and figure out how we can solve this. Okay, so if I, for my first part here, I know that F, oh yeah, it's 5. I gave it away. Okay, I know that F equals what for the first part? 14. Okay, F equals 14. R equals 10, which is really 0.1. No, it's not. No, it's not. No, it's not. Sorry, wrong one. Just 10, because it's still meters. My bad. Okay, so let's go ahead and plug in. 14 equals G times M1, M2 over R squared, so 10 squared, which is really what? 10 squared is 100. Okay, so are we clear up to this point?
Yes.
Okay, so let's go ahead and multiply this 100 up just to get rid of it. So that gives us 1400 equals G times M1, M2. Okay, and I can plug in G and I could divide it over if I wanted to, but I'm not going to for right now. Okay? So let's just take a look at the second one now. 56 newtons equals G times M1, M2 over R squared. And what am I solving for on this second problem? I'm solving for R. So now I got all kinds of variables that I don't have. So if I want to solve for R squared, I'm going to multiply it by it here, multiply by it here to get it by itself. And then I'm going to divide by 56 to get it on the other side, okay, to get R by itself. So now I have R squared equals G times M1, M2 over 56. So what can I substitute for this G times M1 times M2? 1400. Okay, right here I found out for the first problem that 1400 equals G times M1 times M2. So now I'm going to take this and make R squared equal to 1400 over 56. And I'll make that equal R squared. Okay. Then I'm going to divide 1400 by 56 and get 25. I take the square root of that and I see that my radius equals 5. So for those of you that got 40, the proportion worked out right, but what we didn't take into account is that it's really proportional to the reciprocal squared. Okay, it's not proportional directly. It's proportional to the square. So we've got to be careful when we do that. Also, let's think about if the force of gravity increased as these two things moved, what do you think that has to happen to their radius? It gets bigger or smaller? Smaller. If the force of gravity increased, that means they had to have gotten closer together. So our radius should have gotten smaller, which it did. Force of gravity acting on a 2,000 kilogram spacecraft when it orbits Earth 2 radii from the Earth's center. Okay, so the radius of the Earth is 6,380 kilometers, which we know must be in meters, so that means we need it to be 638,000 meters, or 6.38 times 10 to the 6th meters is the radius of the Earth. Okay, and that's from the center to the Earth's surface. That's what the radius is talking about. Okay, our new equation is F equals G times M1 M2 over R squared. Now one of these masses is going to be the mass of the Earth. Okay, that will be kind of taking into account here. So if we plug in our equation, we're going to get 6.67 times 10 to the negative 11th times M1, which we'll say is the mass of the Earth, times M2, which is the satellite mass. And then for the bottom part, what do we need to do if it's 2 Earth radii from the center? Yeah, we just multiply it by 2. So we're going to take 2 times 6.38 times 10 to the 6, and then we'll square that whole portion of it. Okay, we'll square this whole term. It's 10 to the 6th. 1, 2, 3, 4, 5, 6. Caitlin, what'd you get? That can't be. Did you get a negative number or a negative exponent?
I got a negative, I think it was
I think I've gotten 1, 2, 3, 4 different answers. 5 different answers.
4,893.
48.99. Or about 4,900 newtons. How? All right, let's work through the calculator stuff.
You didn't do parentheses right if you
Yeah, we gotta make sure there's no parentheses.
because it would have squared your 7 and taken it to the 49, which throws you.
Yeah, we gotta make sure that it's squared right. Okay, this is the problem right here, because right here is going to square this term before it multiplies by 2. We want to multiply by 2 first, square it, and then do it. Okay, I got it. I just plugged it in wrong like 6 times. I think I'm wait now. No, I still got the same answer. Oh, we have to square the bottom. Okay, let's plug it in. See, I just plugged it in wrong. Make sure you're doing this part. Here we go. This is
Well, eventually.
I just put my parentheses like I put fat spots.
Okay, what questions do you have about this one? Okay, make sure that if there are more than one term, right here, that we add parentheses before the squared, okay? Because we need to get this whole term figured out, and then we square the radius, okay? Because we have to figure out the true radius, and then we can square it. Yeah, Katie?
Well, mine's like close, but not. I got.
I want to see if that's
Oh, I did get it.
All right. All right, we're going to walk through, listen. Okay, if we can't handle what we're sitting, we will change it. Please don't make me do that. Okay, we're looking at the net force or the net gravitational force on the moon due to gravity from the Earth and from the sun. Okay, we're going to assume that both of those are right angles to the moon. So this is kind of what our system here looks like. Okay, here's the moon. Here's the Earth over here. And here's the sun somewhere down here. Okay? We have gravitational pulls on the moon from each of these. So we want to find essentially where the moon will actually be ending up, how far these are both pulling it either way. Okay, so this is what we want to end up finding is this resultant vector here. We're going to call this one towards the Earth the force of gravity on the moon given by the Earth, so F sub ME. And this will be force on the moon due to the sun, so F sub MS. I'm going to get all these put up here and then we'll start working through it. Okay, so here's a bunch more constants that we need to know. No, you can write these down. They'll be given to you. Okay, so the first one is mass of the moon. Second one is mass of the Earth. Third one is mass of the sun. Okay, and then the distance from each of those. Okay, so now we're going to find force on the moon due to the sun. G times M. Mass of the sun times mass of the moon over R squared. So make sure on the distance from sun to the moon we've changed it from 1.50 times 10 to the 8th to 10 to the 11th because I had a typo there. And then we're going to plug into this equation to solve for gravitational force on the moon due to the sun. 4.34 times 10 to the 20th. Is that pretty close? Or just 4.3? Somewhere around there? Okay. So are we clear up to this point? Yes, no, kind of? Okay, so we've done our first two steps. We found this vector, and we found this vector. Now we need to find our resultant. Okay, I'm not kidding. Yeah, we just add them now. Add them. We're gonna build our new triangle. Okay, so we have our Pythagorean Theorem. So we have our force due to the moon and the sun, force on moon due to the earth. We want to find our resultant here. And the angle. So we need to find our hypotenuse and the angle, and that's it. By finding our hypotenuse, it's going to tell us where the moon is actually ending up based on these two poles. Okay, these two gravitational forces from each of these bodies. I got 4.77 times 10 to the 20th. Good, good. At 24.6 or so degrees. Okay, so listen, will this angle have any coordinates? Not really, okay, because we're in space, so we're not dealing with north, south, east, west here. We're dealing with poles in a different direction. It's going to be at about 24 degrees from where it starts. Okay, we don't have to label this east of north or whatever. Okay, we don't have any of those. To get 24.6, we took this angle right here, theta. So we took second tangent of this divided by this. Okay. Okay, to get to our new acceleration due to gravity equation, we're going to start with our force equation that we learned today. So F sub g equals m1 times m2 over r squared. We're going to manipulate that equation. Since we're dealing with things on the Earth's surface, we automatically assume that one of our objects is the Earth, right? So that means we need to assume that m sub 1 is going to equal the mass of the Earth. Okay, so all we did was substitute m sub 1 in for m sub e, which is m of the Earth. Okay, so we're going to substitute m1 in for m sub e. Okay, again, the process of getting here is not as important as the final equation, so it's okay. We're going to substitute in m times g for fg, okay, because we know f sub g equals the force due to gravity. So we're going to go back to our very, very original mg equals f sub g, and we'll substitute that in right here. The mass that we substitute in here is the mass of the object, not the mass of the Earth. Okay, it's the mass of the individual object. All right, and our very last substitution is to cancel m2 on each side. So here we have mass of the object and mass of the object. So when we're looking at the acceleration due to gravity on the Earth's surface, we really don't even care what the mass of the object is. Okay, we're looking at the acceleration due to gravity at a certain point above the Earth's surface. Okay, at a certain radius from the Earth's core. So the mass of the object really doesn't matter. So this is our new equation that we need. Little g, or acceleration due to gravity, is equal to the gravitational constant times the mass of the Earth over r squared. All right, did everyone get that last equation? We're good? Okay, so let's go ahead and find the acceleration due to gravity on Mount Everest. Yep, acceleration due to gravity is little g. We're going to use the equation g equals big G times mass of the Earth over r squared. Okay, so what would be our radius here? Okay, not quite. The 8848 has to be added to the radius of the Earth. Okay, so we know the radius of the Earth. I gave it to you in a previous problem. What was it in meters? Yep. Okay, this was our radius of the Earth in meters. We have to add to it the height of Mount Everest to get to our actual radius, okay? Because this distance right here is the distance from the center of the Earth to its surface. This distance is from the surface to the top of Mount Everest. So we have to add those two together to get our total radius. So we'll get 638,848 meters.
Oh my.
Is our radius. Okay, now we just plug it in and go. Before you finish the math, do you think the gravity will be higher or lower on the top of Mount Everest than on the surface of the Earth? Yeah, lower. As we get farther away from the center of the Earth, it should be lower. Okay, the force due to gravity decreases. What'd you get, Olivia?
I got 6.24 times 10 to the negative 7.
That's too low. Try it one more time. Too low. What'd you get, Madeline? Okay. I got 9.77.
Okay, 9.77 is 10 to the second.
Mm-mm.
What is it? 9.77.
9.77. Okay, and what would our units be here? Yeah, good, no, meters per second squared. Okay, so we can find satellite orbits acceleration just using our circular or our centripetal acceleration equation we learned the first day. Okay, we already have those. We're working our way to this last one here. Okay, to find the force holding it in its orbit, we can use Newton's second law and our equation for centripetal acceleration, which is centripetal force equals mass times centripetal acceleration. We already know this equation also. Okay, I'm going to show you that we're going to combine them to eventually get here. Okay. So since the force of gravity is the only thing that's holding these satellites in their orbit, we can combine equations. Okay. We're going to combine equations for, we're going to combine equations for centripetal force. That's the equation we learned today. And it's right, sorry, I'm kind of out of control. It's right here. And our mass times centripetal acceleration is right here. Okay, so F sub r transfers to this new equation we learned today. M sub a times centripetal acceleration transfers to this. So I'll clear that off so you can see it. This M right here, this first M, is the mass of the satellite. The second M, which is M sub e, is the mass of the Earth. It doesn't make any difference what order these two are in. It makes no difference. Okay. So this is a new equation that we're going to have for things working with satellites, okay, or things in orbit. M is the mass of the satellite.
What is the M on the right side?
Still mass of the satellite, yep. But are you talking about this one right here?
No.
This one?
Mass of the-
Yep.
Talking about that.
Both of these are mass of the satellite. Okay? Alright, let's try one. Okay, we're going to determine the height above the Earth's surface a satellite must orbit in order to stay at the same point on the equator during the whole orbit. Okay, they call these satellites geosynchronous satellites. Okay, geosynchronous because they stay in the same spot on the equator the whole time. Okay, the same position on the equator. We're going to use this equation here to solve for our height. Okay, if we're going to solve for height above the Earth, what does that mean? What variable does that mean we're going to be solving for? Radius. We're going to be solving for radius. Okay, so I plugged in M satellite here, MSAT, okay, because that's the mass of the satellite. You can leave the subscript off if you want. That's totally up to you. Okay, I just plugged it in so you would kind of see it. We want to find R. And the way that we can get there, if we want to solve for R, we don't know mass of the satellite. We don't know R. We know G. We know M sub E. We don't know velocity. Okay? So how do we get to velocity of the satellite? Okay? The reason we know that T is going to equal 24 hours is because it's moving at the same speed as the Earth. Okay? Since this is a geosynchronous satellite and it's staying at the same point on the equator the whole time, it means it has to spin the same speed as the Earth. Okay, so the T, or the period, is going to equal 24 hours. So we can plug in our equation for velocity as a substitute for V in this equation. Okay, and we can cancel out mass of satellite on both sides. So that makes our actual final equation. Yeah, I'll zoom it in. This bottom one.
Do we need to put that on our note card, or is that just for this problem? Do we need any of the top stuff?
Not really. I'm just kind of showing you how we get there. I don't think it won't hurt to have this one in your notes. I don't think it's probably note card worthy.
The one on the bottom?
The one on the bottom, you'll have to use it for this problem. It wouldn't be bad to have on your note card. I don't really honestly know how often we'll use it. So it's up to you. If you have room, it won't hurt, but...
Why is the top one squared? Oh, is it these?
Yep. I'm going to talk to you why it's squared, okay? So velocity, our velocity equation is V equals 2 pi r over t. Oh, sorry. Okay, so let's look at why this equation looks like it does. Okay, right here. Velocity is 2 pi r over t. In this equation, velocity was squared, right? V squared over r. So we have to square this whole term in order to put it into this equation. Okay, so we take 2 pi r squared and we square t on the bottom. We took velocity out because we weren't given velocity, but we know what t is. So we're able to work with that.
Is the equation on top, can't we always cancel the m out on both sides?
The M satellite, you can cancel it out. We could have done it earlier.
It needs to be there on the normal equation, because you're going to take it out every time.
On the normal one, you mean? Like,
the one you gave
tell
us
me
a
what...
slide ago that was where you combine them, and there's an m on both sides. Can't you take out an m no matter what?
Like right here?
Yeah.
Like on that bottom one?
Yeah.
Yeah. Yeah, you could.
But m's on both sides and on the
Yeah.
Irrelevant.
Okay, so let's go ahead and plug in numbers and let's solve for this. All right. So we're going to solve here for radius. We know G. We know mass of the Earth. and we know t. What's the period here? 24 hours. What unit does it need to be in? Seconds. So we need to send 24 hours to seconds. So in order to do that, we're going to multiply by 3,600. Yep. So now we can go ahead and start plugging in here. We're going to solve for radius. This one takes quite a bit of math, so you're going to have to kind of leave some room on your sheet if you haven't. Yep, yeah, go ahead. I'm going to walk through, because it takes quite a bit of manipulating the equation, so if you want to follow along up here, you can. If you want to do it in your notes by yourself, you can. Okay, so all I've done thus far is plug in numbers. Okay, this is what your equation should look like with every number you know plugged in. Now I'm going to actually start doing some math here. And the math takes quite a few steps to get through. On which part? Okay. Everyone see where I'm going thus far? Or not so much? So I moved r squared from one side to the other, and I'm going to combine those two terms. Okay, so now I can go ahead and cancel one of my r's, and I'm going to make this r to the third. And I need to multiply this up to get it into the numerator. So I'm going to take 3.98 times 10 to the 14th times 7.46 times 10 to the 9th. And that gives me 2.98 times 10 to the 24th equals 4 pi squared r cubed.